Okay, welcome to one of our videos on a fairly big topic in the forces unit called, well, really it's about what to do when you have an object that's on a ramp. Now, this is the extent of where the Regents class gets to. They deal very briefly with forces on a ramp, but this for us is kind of like right in the middle of our unit. Okay, forces on a ramp for Regents is like the hardest thing they do. This is going to be, you're going to get so much practice with this that this is not going to be that substantially difficult, but it is a little tricky when we start off. One of the reasons that it's tricky is because you have to deal with objects on a ramp a little, I don't want to say fundamentally differently, but there's one thing that you have to remember to do, and that is to tilt your axes to align with the object's acceleration. And I'll get into what that means in a second, but the other important thing to remember is that as a consequence of this tilting of the axes, sine and cosine switch. And again, I'll get to what that really means in just a second. Here's our example that we're going to be working on today, or our first example. A box is placed at rest on a ramp as shown below. The ramp surface is frictionless. So we've got this box on a ramp here. Now, normally, and I don't want to say, well, in a lot of cases, what we'll do is we'll draw a free body diagram and we'll draw an axis so that we know what directions to, or what directions we're using so that we can break up our forces into forces in the x direction, forces in the y direction, etc. And most of the time, your axis might look something like this. If I didn't give you, this is kind of like pointer, you might do something like this, where this is the x direction, this is the y direction. They're both positive, okay? Now, I'm not saying that this is wrong. You can always set your axis to be whatever you want, but you do not want to do this if you have an object on a ramp. The reason is this is going to make your life much, much, much more complicated, because I want you to think about what this object is going to do. If the ramp surface is frictionless, this object is going to slide down the ramp and it's going to accelerate as it goes. My question to you is, which way is it accelerating? You might say, well, obviously it's accelerating in the positive x direction, but the box is not moving just in the positive x direction. It's also moving in the negative y direction. And since, let's see, the box is accelerating as it goes down, doesn't that really mean that it's accelerating both in the positive x direction and the negative y direction as shown here? It really does. That means we have two different equations that we have to deal with and two different accelerations. And I'm just going to tell you right now, that's going to make your life very complicated if you were to analyze something like this. Here's what we do instead, okay? Let's say that we're drawing our free body diagram for our box. So remember, we're going to draw our dot. We're going to label it as box. Now we're going to draw our axis. You always want, and maybe this got a little bit lost in the shuffle in the last video, but you always want to line up your axis so that it is aligned with the direction of the object's acceleration. In this case, the object is accelerating down the ramp. So what that means is we should make the acceleration, or we should make our axis also point down the ramp. That would look something like this. Remember, an axis, you still have to have the two directions on the axis be perpendicular to one another, but you can tilt that axis in any way you want so that you can line it up with the direction of acceleration. So we're going to say that the positive x direction is down the ramp. The positive y direction is perpendicular to the ramp surface and up off of it. Trust me, this is going to make your life much easier. Now that we've got that drawn, we can worry about the forces that are acting on our box. This box clearly has a force of gravity on it. That's why it's on the ramp in the first place. It's being pulled down towards the Earth's surface, or towards the Earth's center due to gravity, the force of gravity. And that force always points straight down if we have something at the surface of Earth. That looks like this. Okay, so that's Fg. And there's only one other force on this box. There's no friction, since the ramp surface is frictionless. There's no applied force, it doesn't look like. No one's pushing this. There's no tension. There's no springs or anything. There's only one other force, and that results from the ramp itself. That's the normal force from the ramp onto the box. And that's perpendicular to the surface that the object is resting on, which means it's in this direction. So there's my two forces, Fn and Fg. Now you might say, okay, well now it's time to go and make our net force equations. We have to write those out. Well, we have to do one thing before that, and that one step is actually going to take a few minutes here the first time I explain it. The reason we can't write out our net force equations yet is because one of our forces is not in either just the x direction or just the y direction. Take a look at Fg. Actually, first, take a look at Fn. That's very clearly in the positive y direction, but Fg is neither in the positive or negative y direction or positive or negative x direction. It's kind of in a combination of both. If you turn your head and you look, you can see that Fg is partially in the positive x direction and partially in the negative y direction. In other words, we could break this force up, this Fg, into components, which aren't new forces by themselves, but just two different aspects, perpendicular aspects of the same force, and we could write it this way. We could break this up into a component that looks like this, and a component that looks like this. And again, if we add those components back together, you would get this Fg force. The reason we're doing this is because now, once we name these forces, then we're going to be able to write the net force equations for the x direction and for the y direction. But we do have to name them first. Remember, a component is always named, or you can figure out the size of a component, the magnitude, by taking the original vector and multiplying by either sine or cosine of theta. So both of these are going to start with Fg, but I'm not really sure which one's going to be sine, which one's going to be cosine. In order to figure that out, I have to do a little bit of geometry. I'm going to go back up to my picture because it's easier to sketch up there. And from the center of the box, center of the bottom of the box, I should say, right here, I'm just going to draw a straight line going down. Notice what this does, and notice the shape I had for this ramp in the beginning. It's a right triangle, okay? By drawing a straight line right down, I've made a similar right triangle. It's just a little bit smaller. Similar triangles always have the same angles. So this angle here is going to be the same as this angle, and this must also be a right angle. We're going to do a little math with angles right now. One of the facts that you should have learned in geometry class is that the interior angles of a triangle always add up to 180 degrees. We know this angle, it says theta. We don't actually care what angle that is, okay? It could be anything. So theta and 90, and we don't know what this angle is, okay? We can figure this out though because we know that the sum of the angles has to be 180 degrees. So if we add theta plus 90 degrees plus, I'll just call this x, we can get an expression for what this angle is. If I subtract 90 to the other side, 180 minus 90 is 90 minus theta. I end up with x equals 90 minus theta. That's what this angle is right here. Now, that's interesting. It's not particularly useful to me yet, though, because my whole goal here, I should have mentioned this earlier, when I've got this diagram here, I need to figure out, for these components, which one of these is going to have sine attached to the end of it and which one's going to have cosine. In order to do that, I need to know where on this diagram the angle theta goes. Theta is the angle for this ramp, okay? That's the angle that the ramp makes with a horizontal. Turns out that I need to be able to put theta on here somewhere, and once I do that, it's very easy to determine which component is sine, which one gets cosine. So right now, as you look at this, you might be able to kind of tell, well, this angle right here is 90 minus theta. It's between a vertical line and the ramp surface. That's kind of the same angle, or it is the same angle as this angle right here. This is a vertical vector, and this is a component parallel to the ramp surface. This angle right here is 90 minus theta. But we don't want that. We want to know where theta is. So here's what we're going to do. I'm going to draw another line. I'm going to draw a line that is perpendicular to the ramp surface right here, this dotted line right here. If it's perpendicular to the ramp surface, then that means that the angle between the ramp surface to the dotted line has got to be 90 degrees. And if that's 90 degrees, that means the sum of this angle and this angle has to equal 90. Which means 90 degrees, the total angle, has to equal 90 minus theta plus x. I'm going to solve this equation for x again. Subtract 90 from 90, I get 0. Add theta to the other side. It turns out that this angle right here is actually equal to this angle down here. Okay? And the reason that's important is because if you look at this angle right here, here's a vertical line, here's a line, this dotted line is perpendicular to the ramp surface. Here's a vertical vector. Here's a component that is perpendicular to the ramp surface. This angle here is the same as this angle here. This angle is actually theta. The ramp angle appears geometrically right here. Okay? The first couple times you do that, you're going to have to go through all of those thinking steps. Once you get used to this idea, though, you can get through this in about 20 to 30 seconds, okay? Or when you get really, really good, you can usually just kind of look at this and tell where the angle is going to go. Now, how does that help us with sine and cosine? Well, we know that cosine is always associated with the adjacent side, and adjacent means next to. So the component that gets the cosine attached to it is always the one that's next to the angle. If you look at this component, it is directly next to our angle, so this component is FG cosine theta, which means the other one has to be FG sine theta. Now take a look at that for a second. This is a little strange because usually when we first started talking about vectors and components, you know that we said that when we found the x and y components, to find the x component you always used cosine, to find the y component you always used sine. Take a look at this. This is not the case here. The y component of this vector in the negative y direction is found by FG cosine theta, whereas the x component is found by FG sine theta. Okay, that's what I mean when I say sine and cosine switch. Now, if this was a Regents class, I would just tell you to memorize that. In AP, you really need to understand why that happens. If you don't get it right now, that's fine. You might want to go back and rewatch the video a little bit and see where you're losing understanding, or you need to come to me in class with questions and we can figure out, and we can practice and we can talk through it so that you understand. In any case, our free body diagram is now finished. Okay. Oh, and before I actually move on, one more thing. So another way to remember this is that the angle theta will always end up on a ramp question showing up between the actual component of the force of gravity, Fg, and the component that's perpendicular to the ramp surface. That's this one right here. That's where theta has to go. And once you know where theta goes, you can write out which component is the one that has cosine attached to it, which component is the one that has sine attached to it. Okay, so again, we did all of that just so we could write out our net force equations in the x and y directions. If we didn't split this up into components, we wouldn't be able to do that. Okay, it's very, very important that before you write net force equations, your forces are all in directions that are aligned with your axis. If you have a force that's not aligned with your axis, you have to split it into components, and those components will be aligned with the with the axis. Let's write our net force equations. F net y equals, in the positive y direction, Fn minus negative y direction, Fg cosine of theta. Now we know, I mean, if you just think about it, this box is very clearly not going to start blasting off of the surface or sinking down into the ramp. That means that when we finish out this equation, we write equals may. There is no acceleration in the y direction, so this is 0. We end up with Fn equals mg cosine theta. Okay, the normal force is not just equal to mg in this case. It is in a lot of cases, but it's not equal to mg in this case. It's equal to m times g times the cosine of theta. Okay, so it's actually, since cosine of theta is going to be less than 1, it's going to be a little bit less than normal. In the x direction, we have just Fg sine theta. It's the only force in the x direction. It's in the positive x direction. That's fine. It's fine it's the only force. Equals max. Now, there's a neat little relationship here. Since Fg, the force of gravity, one of the equations for that is mg. I'm going to write that in. Mg sine theta. So just make a little substitution. Equals max. If you'll notice, if I divide both sides by m, the m's will totally cancel out. And what I'm left with here is ax equals g sine theta. Okay, so the acceleration is only dependent on the acceleration due to gravity and the angle that the ramp is at, since we're taking the sine of that angle. I'll get back to that in a second. Let's plug in what's the acceleration of the box down the ramp if the ramp angle is 25 degrees. Well, I don't have to go through all this. I have my equation for the acceleration. I've derived that. So now I can just write ax equals g sine theta. Ax equals, we use 10 meters per second squared, times the sine of, 25 degrees. Make sure you're in degrees as always, or as always to this point. Sine 25 times 10. The acceleration down the ramp at this angle would be 4.23 meters per second squared. Okay, we can actually test this in class and we'll get results that are very, very close to it, within 10%. Hard to get a perfectly frictionless ramp, that's why it's not perfect. How would the acceleration change if a box that was twice as massive is used instead? So how would the acceleration change? Take a look at the acceleration equation, g sine theta. Is there any mass term in there? No. Interestingly, it doesn't matter what the mass of the box is, the acceleration is going to be the same in any case. It's kind of like how free fall acceleration is 10 meters per second squared, regardless of what the mass of the object that's in free fall is. This is a very similar case. So how would the acceleration change? It wouldn't change, since there is no m in the equation for ax, the acceleration. Now, those of you who are familiar with Newton's second law, F net equals ma, the net force equals the mass times the acceleration, might be scratching your heads and saying, wait a second. If you made a box that was twice as massive, and why wouldn't that change the acceleration? You have an m in that net force equation. That is very true. Usually, when you increase m, that decreases the acceleration. But look what else is in that net force equation. The net force in that direction, in the positive x direction, was Fg sine theta. Fg is the force of gravity, and Fg is equal to the mass times the acceleration due to gravity. So look what happens. Even though the mass increases over here, and typically that makes the object have more inertia and be harder to accelerate, guess what also increased? The force. The box got harder to accelerate, but the force on the box also grew. So even though the mass went from m to 2m, the force of gravity went from Fg to 2Fg. So these factors canceled each other out. And that's why the acceleration is independent of the mass. That's how we'd say that. We're going to go to a slightly different example, a little bit more complicated. We're going to add some stuff in now. A box on a steep ramp is attached to a rope that will pull it up the ramp as shown below. There is some friction between the box and the ramp. Okay, so now we've got friction and we've got this rope pulling up the ramp. I'm going to start with my free body diagram. Okay, here's my box. I'm going to tilt my axis again since I have an object that is being pulled up a ramp. It might be accelerating up the ramp. We don't have that information yet. So this time I'm going to make my axis so that the positive x direction is up the ramp. There we go. Now the force is on the box. Same as last time, we still have a force of gravity on the box, Fg. We have a normal force on the box, Fn. We have tension pulling the box up the ramp, T. And we have a force of friction. Imagine what would happen to the box. Even if there wasn't friction, the tension would presumably pull the box up the ramp, and we're told it's pulling up the ramp. So friction must point in the opposite direction as that. That means down the ramp. So this is F. T is in the positive x direction. Fn is in the positive y direction. Ff is in the negative x direction. So far, so good. But look at that force of gravity. Anytime you have a ramp question, the force of gravity is not going to line up with your tilted axis. So what do? We have to break it into components. Okay? We're not changing the size of the force of gravity. We're just rewriting it in a way so that we can write net force equations. Okay, so there's my components. And again, we can do the same sort of math. We could say that, let's see, if this box was up here, this angle is theta, 90 degrees. This has got to be 90 minus theta, which means this is going to be theta. Theta shows up over here. Okay, if you're still confused on that, I would just go read and watch that video, or we will get lots of practice that in class. Make sure you let me know. This component down here, since it's adjacent, it's right next to the angle that we drew in our free body diagram, has to be Fg cosine theta. By the way, you have to label this angle theta in your free body diagram, otherwise it will take points off. This is Fg sine theta over here. Now I'm ready to write my net force equations. F net y equals, in the y direction, Fn minus Fg cosine of theta equals MAY. Same thing in this case. The box is not blasting off of the surface perpendicularly or sinking down into the ramp. The acceleration in the y direction is 0. Therefore, Fn, just like last time, is equal to I'm going to write mg cosine theta. And notice that this is the same thing as last time, like I said, and we didn't have any different forces in the y direction, so that makes sense. The x direction is much more complicated this time, so we have two additional forces in the x direction. Okay, something to point out about here that I missed a minute ago. Sometimes people get freaked out. They see two forces or two vectors pointing in the same direction, and they say, oh, we can't have that. Sure you can. You can have as many forces pointing in as many directions as you want, okay? Just so happens that a lot of times there's only one force in our very simple examples that's pointing in a certain direction. So this is fine. Another thing people try and assume is they see two vectors pointing in the same direction. They assume that they're the same magnitude. That's not true at all. These forces are completely separate. They're completely different. This is a force of friction pointing down the ramp. This is a component of the force of gravity. They don't have to be the same. They don't even have to be close to each other. So anyways, back to the free body diagram. The net force direction in the net force equation in the x direction is T for tension, that's in the positive x direction, minus the force of friction, minus Fg sine theta. Both of those get minus signs because they point in the negative x direction, equals MAX. Now you could leave it there. I'm a big fan of writing things in as simple terms as possible. By simple, I mean like the most fundamental terms, like not necessarily force, but if we can break that down further into mass and acceleration due to gravity, etc., then I usually think that's a little bit easier. Makes the equations a little bit longer, but it also means that sometimes you can cancel things out and you can see relationships a little bit more clearly. I'm going to do that for both of these, for this case. Tension can't be broken down into anything else at the moment, but the force of friction, since this object is sliding up the ramp, we know it's kinetic friction, which means we should be able to use this equation, mu Fn, mu being the coefficient of friction, Fn being the normal force, minus, I'm going to change this Fg into an mg sine theta, equals MAX. And we can actually go a step further because we just solved for what Fn is. Ultimately, I can write this as T minus mu mg cos theta minus mg sine theta equals MAX. And I'm going to go one step further than that. I have an mg in both of these terms. I'm going to take it out. You don't have to do this, but I like to do this sometimes. I'm going to remove it from both these terms, write it out front, and then, so it's kind of like the reverse distributive property. Mu cosine theta, since I'm taking out a negative mg plus sine theta equals MAX. Again, you can stop at any of these points if you want to, okay? Especially 1, 3, and 4. These are just different ways of writing the same thing. I prefer to write things, to expand things out as much as possible to get them in as simple terms as possible. Now to plug in. If the coefficient of friction is 0.22, the angle is 50 degrees, and the force of gravity on the box is 200 newtons, what is the necessary tension in the rope to pull the box up the ramp at a constant velocity? So now we're just taking this equation and we're plugging in to find the tension. Rewrite the equation first. We're told constant velocity. That implies no acceleration. So if this is 0, I'm just going to move this entire term to the other side. It's going to give me T equals mg, parentheses, mu cosine theta plus sine theta. And now I can plug in and solve for T. I know what mu is. I know the angle. You might be a little concerned. Wait, I don't know what the mass is. I know what g is. But you're told that the force of gravity on the box is 200 newtons. Remember that force of gravity, Fg, is equal to mg. So that means since the force of gravity is 200 newtons is simply the product of m and g. As long as I write this and show how I know what m times g is, I could plug 200 right into there without having to go and figure out the mass and all that stuff. 200 newtons times, in parentheses, 0.22 times the cosine of 50 degrees plus the sine of 50 degrees. So I'm going to start inside the parentheses, take the cosine of 50 times 0.22. Then I'm going to add the sine of 50 to that. I get 0.9 something, multiplied by 200. I end up with a tension of 181.5 newtons. Let's consider the practical applications of that for a second. We use ramps to move heavy things up distances that it would be hard to move directly upwards. Like imagine if you had to pick up this box. The box is 200 newtons. That's like, okay, that's pretty heavy. If we want to pick it straight up, we need to apply a force of at least 200 newtons to make sure it gets where it's going. If we use the ramp, on the other hand, to make sure that it gets where it's going, we only need to apply a force of 181.5 newtons. It reduces the force by about 10%. Now, if that might be useful to you, it might not. Perhaps if there was a smaller coefficient of friction or if the angle was lower, this would be a smaller tension. But the fact of the matter is this ramp reduces the amount of force needed to pull something up to a higher height. That's why we use ramps. So this is somewhat useful. Doesn't reduce it a ton, but it does make it easier to pick up the box or move it to a higher spot. Okay? We wouldn't want to use the ramp. It would be a useless ramp if there was enough friction on there that made it so that the tension required to pull it up was bigger than the force required to just lift it up to like pick it straight up using just your hands. Okay, that wouldn't be a very not useful ramp. Let's look at another case though. What is the necessary tension in the rope to pull the box up the ramp at a constant acceleration of 1.5 meters per second squared? So how much force, instead of just pulling up at a constant velocity, how much force would be needed to cause it to accelerate up the ramp? We're going to go back to the same equation, T minus mg, parentheses, mu cosine theta plus sine theta equals max. We now have a different tension. If you think about it, we're trying to make it accelerate up the ramp. You could probably predict that the tension's probably going to be a little bit higher. We still know what mg is. That's 200. Mu, theta, we know all that. In order to solve, well, we know the acceleration, but we need to know the actual mass. Now, that might cause you to stop for a second, but we know 200 is equal to m times g. We go back up here, we know what g is. Since g is 10 meters per second squared, it makes it very obvious that the mass is 20 kilograms. Now I have everything that I need to plug in. So I can write T minus 200 newtons times 0.22 times the cosine of 50 degrees plus the sine of 50 degrees equals 20 kilograms times 1.5 meters per second squared. This bit is all the same as it was up here. 200 times, in parentheses, 0.22 times cosine of 50 plus the sine of 50. That's still going to end up being 181.5 newtons. None of that stuff changed. But in order to solve for t, I'm going to have to add that to the other side. On the other side is 20 times 1.5. 20 times 1.5 is 30. Add that to 181.5. I get that the tension has indeed increased. It is now 211.5 newtons. 30 newtons more. Where'd that 30 newtons come from? The problem kind of stated that the net force required to make this object accelerate at this rate would be 30 newtons. Where's that extra 30 newtons going to come from? Just because you want it to accelerate, that's not going to change the force of friction. It's not going to change how much gravity pulls on it. That means the tension had to increase. So, in order to make the net force be 30 newtons, we had to increase the tension by 30 newtons, which is why this tension is now 30 newtons bigger. Okay? You will get lots of practice with ramps. Once you get used to it, ramps become very, very second nature. That's all for this video. Our next topic is going to be on a topic that Regents does not touch on. This is going to be objects or systems where you have two different objects that are somehow connected, and drawing free body diagrams and analyzing situations for those. If you have any questions, please let me know, and I'll see you later for that video.